Alright, for the last few videos we've been working with the law of signs. And in this video I want to introduce you to something called the ambiguous case. First of all, real quick, what does ambiguous mean? That's sort of an SAT word that plays into this mathematical context, but it's a word in the English language. So, hey Siri, what does ambiguous mean?
Ambiguous means a language open to more than one interpretation, having a double meaning.
Thanks, Siri. Well, there you have it. Having more than one meaning, open to interpretation. So, as we work with the law of signs here, the ambiguous case is going to be a case where there's more than one possibility, and we're going to have to do some calculations to figure out exactly which situation we're in. Remember back in geometry when we used to prove triangles congruent by side, 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 and things like that? Well, there are three sets of information that we can be given where it's useful to solve the triangle using the law of signs. And one of them is when we have angle, side, angle. If you see that set of information, two angles and the included side, that you're going to want to use the law of signs to solve that. Another situation where we have two angles and a side would be angle, angle, side. Alright, two angles and the non-included side, we still will use the law of signs for that. But then there was that situation where it could not be used to prove that two triangles are congruent. And the reason why we could not use side, side, angle to prove that two triangles were congruent is because this is the ambiguous case. We're going to find out that the triangle could be a lot of different things depending on exactly the calculations that we have. So that's why it didn't prove two triangles were congruent, because this is the ambiguous case. Now, I really want to emphasize this to you because once I teach you about the ambiguous case, a common mistake is for students to, from now on, think that everything is the ambiguous case. So please understand that we're just talking about side, side, angle. If it's not side, side, angle, it's not the ambiguous case. Now, let's look at the first two situations. The ones that are not ambiguous. So if I give you the measure of angle A, let's see, so that would be 42. The measure of angle B is 51, let's say. Alright, so angle B is 51 degrees. And side C is 12 feet. Alright, side C has to be across from angle C, so I'm going to put the 12 right here. So you can see this is the angle, side, angle situation, and I could use the law of signs to solve this. By the way, this is the law of signs. The sine of an angle over the opposite side will equal the sine of another angle over its opposite side, which will equal the sine of another angle over its opposite side. These ratios are all equal. Sometimes you'll see these written in the reciprocal way, like A over sine A is equal to side B over the sine of angle B, which is equal to side C over the sine of angle C. This is the same thing. So again, we could use the law of signs to solve this because this is the only way that this triangle could look. Similarly, if I give you the measure of angle A is 42 and the measure of angle C is 51 and side A is 12. Side A would be across from angle A, so the 12 would go right here. So again, you've got your angle, angle, side, and again we could easily solve this using the law of signs because this is the only way this triangle could look. Now, compare these two cases, angle, side, angle, like this, angle side like this to the infamous side angle, aka the ambiguous case. Now, again, ambiguous means there's more than one possibility, and that's what I'm going to illustrate here. So really, I'm giving you the same type of information in every case. I'm giving you angle A, and side C. But you're going to find out that even though I'm giving you those same three pieces of information, it's going to turn out completely differently in all four of these cases. In fact, it's going to be so wild that I can't even draw in the third side. I have to leave it this temporary dotted line because we don't even know what's going to go down. Alright, well, let's get started. Looking at this first situation, if the measure of angle A is 36.9, so this would be 36.9, and side A is 5, so that would make this would be the 5 over here, and side C is 10. So this is what we know. Now, you might think, oh, it's just a normal problem. Let's just do the law of sines and figure this out. But here's what makes this problematic. We have to think about the height of this triangle. Alright, so imagine that I were to drop a vertical line straight down. Okay, think about the height of this triangle. Now, this is forming a right triangle over here on the left, and so I could set up the sine function, meaning opposite over hypotenuse, in the following way. Couldn't I go, you know what, I feel like using green right now. Couldn't I go like this? The sine of angle A, the sine of 36.9, should equal opposite over hypotenuse. So that should equal h over 10. Now if I were to multiply both sides by 10, that would give me 10 sine 36.9 is equal to h. So I'm just going to put this in my calculator real quick and see what I get. Alright, here we go. 10 sine of 36.9, and boom, that gives me 6.00. Okay, so the height is 6. So look, we just found that this height is 6. So I'm just going to go ahead and replace this h with a 6. Now, I need you to see why this is a big problem. Now, see this side over here? This is length 5. Okay, so I made it dotted so I could adjust it and swing it around and see what's going on. But what we know for sure is that this has a length of 5. Now, if this has a length of 5, but the height of the triangle is 6, is this going to actually reach the ground and make a triangle? And of course the answer is no. The distance all the way down to the ground here is 6, but this length of this so-called side is only 5. It will not reach the ground. This will not form a triangle. So we have this side angle information that we're given, but in this case what happened was we got no solution. No triangles can be formed. Let's see, I think I'll just write it right here in green. No triangles. Okay, so there's no solution. Now let's take a look at the next case. So it's very similar to the one that we just had, and in fact we can use some of the same information. But again, angle A is 36.9, so this is still 36.9, and Side A is 6 this time, so this is now going to be 6. You can probably see where I'm headed with this. And then side C is again going to be 10. So the only thing I'm changing is side A. The other two things are staying the same. Okay. Now, because the angle is the same, and because the hypotenuse is the same, if I were to drop a perpendicular line down, like I did before, this is going to be 6, just like it was before. So, now I see that this side A is length 6, and the height of the triangle is length 6. So I have left this as a temporary side so that I can move it around and swing it and see what's happening. But what's going to happen if this is length 6 and the height of the triangle is also 6? Is this going to make a triangle? Well, yes, it will make a triangle, but because they are exactly the same length, alright, this side A is exactly the height of the triangle, then that means that there's only one triangle you can make, and that's the triangle where side A is the height. Alright, they're the same thing, 6 and 6. So it's only going to make a triangle if you make it go straight down, perpendicular, and make the right triangle. Okay, so in the previous case, with the same information, the only thing I changed was the length of side A, but when side A was 5, you had no triangles. When side A is 6, just 1 unit longer, that's the only thing I changed. Now we have one triangle. Okay, I just want to write that down. So this time we have one triangle. Okay, but wait, there's more. So again, everything is staying the same except for side A. So angle A again will be 36.9 degrees. Side C, okay, across from angle C again will be 10, just like it was the previous two times. The only thing I'm changing is side A over here. This time it's going to be 12. Now, based on the calculations that we did the first time, again, this part hasn't changed. If I drop a perpendicular line down, this is still length 6. But now, side A is longer than the height. First it was too short, and it couldn't reach, and so we had no triangles that we could make. Then it was exactly the height, so you could make just one triangle, just barely. But now it's bigger. Alright, side A is bigger than the height. So you can, this is the situation where it would make a normal triangle, an oblique triangle, non-right triangle. Okay, and we could go ahead and solve this using the law of sines like normal, as it turns out. Okay, now, could I make another triangle out of this? Now let me think, because I can move this around. Okay, because I made this temporary so that I could swing this and see. So remember, this is length 12. So right here, it's making this triangle. Now, if I swung it around, could I make another triangle, like maybe here? For example, could I make another triangle if I put it over here on this side? Well, no, because look, this side, side C is 10. And this side that I'm moving around is 12. It's longer than side C. So there's no way it's going to fit inside of here. Alright, that would make it shorter. Because this side is 12, it's longer than side C, it's not going to make a triangle anywhere in here. It's too big to fit in there. The only place it's going to make a triangle is out here. Okay, so it's only going to make one triangle once again. Alright, and this triangle looks like this. So one triangle. So I could just go ahead and solve this using the law of sines. Okay, but there's one more situation that we have to watch out for. And again, just take notice that given the same three pieces of information, angle, side, side, we're getting all of these different situations. So one more time, angle A is still 36.9. Side C over here is still 10 like it was on the previous two problems. I'm sorry, the previous three problems. The only thing I'm changing is side A, which is right here. This time it's going to be 7. We already know from the previous three problems that if we calculated the height of this triangle, it would turn out to be 6. So on the first problem, side A over here was too short to reach, so we weren't able to make a triangle at all. Okay, in fact, let's go back in time. So in the first situation, it was too short. It couldn't reach the ground because this was a height of 6. So no triangles. In the second situation, it was just barely long enough to make a triangle. So it made one triangle, which was a right triangle. But then on the third situation, it was bigger. It was bigger than the height. And so we were definitely able to make a triangle. And we looked to see could we make two triangles. We couldn't because it was too big to make a second triangle if we swing it to the inside. So the question is, yes, we can definitely make one triangle because it's bigger than the height, so it will definitely reach the ground. But the question is there a second triangle that we could also make? And so let's see. If I take the end of this so I can swing it around, would it be possible that this side could also fit in here? Now, the last time it wouldn't fit because this was 10, and then this other side, side A, was 12. And there was no way that 12 was going to fit in here because this was only 10. It would be too big. It would stick out. But this time, this side is 10, but our side that we're swinging like it's on a hinge is only 7. So it will fit in here. So we really could have two different triangles. We could have an acute triangle like this, or we could have an obtuse triangle like this, where this would be an obtuse angle in here. Okay? So if side A is longer than the height, yet shorter than side C, if it's between these two lengths, you can make two triangles out of it. And this is truly ambiguous. In fact, if we were going to solve this using the law of sines, we would have to write two completely separate solutions to represent the two triangles that could be formed. Alright, so that is the end of my introduction. On the next video, we will actually look at some problems where this is going to come up, but for now, I just wanted you to have the overview of the ambiguous case. So if you see that you're dealing with angle, side, angle, that will not be ambiguous. Angle, side, angle only forms one type of triangle. You can make a triangle and it looks like this. If you see angle, angle, side, there's only one possibility. It's just going to look just like this. The only time you have to worry about all of these different possibilities is when you have side, side, angle. Only side, side, angle is the ambiguous case because this last side, alright, the swinging side, if it's too short, if it's shorter than the height, you will have no triangles. If it's exactly the height, then you're going to have one triangle, a right triangle. If it's bigger than the height and bigger than the other side, then you're only going to have one triangle. It won't be a right triangle, but you're only going to have one triangle. But if the swinging side is somewhere between the length of the height and the length of the other side, all right, if the length is between those two numbers, then that's when you can make two triangles out of it, and you will have two solutions. So watch the next video to see this in action.